In this video, we look at sequences as discrete functions. So first off, we have to define what a sequence is. A sequence is a set of elements that are in order, and we call individual elements of the sequence, we call them terms. So each element of the sequence is called a term, and each term has a corresponding term number. Now, term numbers always, the first term would be term 1, the second term would be term 2, the third term would be term 3, so we use the natural numbers as the term numbers. And another thing to note is that sequences can have a finite number of terms, which means that we can count the number of terms in the sequence, or an infinite number of terms. So there's, a sequence would continue like 4, 7, 10, 13, and would just go on forever. So there's an infinite number of terms in this sequence, whereas in this sequence there's a finite number of terms. The sequence stops when the term number gets to, or when we get to the term 73. So this is a finite sequence. And this sequence here is an infinite sequence. So just another thing to note that this would have term number 1, this would have term number 2, this would have term number 3, and this would have term number 4, and so forth. So we start numbering the terms with 1, and then the second term is 2, 3, and 4, and so forth. So here it says we can represent sequences as discrete functions whose domain is the term number and whose range are the terms of each sequence. So what that means is that I can come up with a function that has input that is the term number and whose output is the term that corresponds to that term number. So we're going to look at how to come up with explicit formulas for those functions, where an explicit formula is just a formula that represents any term in the sequence as a function of its term number. So again, the input would be the term number, and the output would be the term. Okay. So let's do a couple problems in relation to what we just discussed and the new definitions that we have. In the first problem, it says, write the first 3 terms and the 20th term of the sequence below. So here we have explicit formulas that represent the nth term in our sequence. So we call this, we say that t sub n represents the nth term in our sequence. So let's go ahead and we'll do some calculations here. So if I wanted to figure out what the first term was, I would do t sub 1. So the first term is represented by t sub 1, which is equal to 1 squared plus 1 over 1. Which is equal to, let's see, 1 squared is just 1. 1 plus 1 is, let me just extend my fraction bar here. 1 plus 1 is 2. 2 divided by 1 is 2. So the first term is 2. The second term, t sub 2, would be equal to 2 squared plus 1 over 2. And 2 squared is 4. 4 plus 1 is 5. So we have that the second term is 5 over 2. And then we have the third term. T sub 3 is equal to 3 squared plus 1 over 3. So 3 squared is 9. 9 plus 1 is 10. So we have 10 over 3. And then we have the 20th term. So t sub 20 would be equal to, the 20th term would be equal to 20 squared plus 1 over 20. 20 squared is 20 squared is 400. 400 plus 1 is 401. 401 over 20 is just 401 over 20. That doesn't simplify. So we have that the 20th term is 401 over 20. So we have that the first term in this sequence would be 2, then the second would be 5 halves, and then 10 thirds, and then the 20th would be 401 over 20. In the next sequence, we have that we use a different notation. We can also use function notation here. So we have f of n is equal to 2n plus 1. So these are just two different notations. So the first term would be f of 1, which is just 2 times 1 plus 1, which is 3. We would have f of 2 is equal to 2 times 2 plus 1, which is 5. F of 3 would be equal to 2 times 3 plus 1, which is equal to 7. And then f of 20 would be equal to 2 times 20 plus 1, which is 40 plus 1, which is 41. So in this sequence, the first term is 3, the second term is 5, the third term is 7, and then the 20th term is 41. In the next problem, we can be given a sequence, and then sometimes it's really useful to... Oh, there should be a comma here. So comma, dot, dot, dot. So one of the things that's really useful is to have a sequence that's written out, and then be able to figure out an explicit formula for that sequence, because then it allows us to calculate the nth term, and I don't have to continue the pattern to get the next successive term. So let's say like I had these 4 terms, and I wanted the 100th term. Well, I wouldn't want to have to write it out so that I get, I go all the way to the 100th term. That's just, it would be a little bit ridiculous. So it's good to have an explicit formula. So here we've got a sequence where we have 2, 7, 12, 17. So one of the things to note here is that we're every successive term we're adding 5. So we have plus 5, plus 5, plus 5. The next term, we're just going to be adding 5. So to get the nth term, let's see here. Well, we have that t sub n. So we've got 2 plus, well, let's see here. So for the second term, I've added 5 once. For the third term, I've added 5 twice to 2. For the fourth term, I've added 5 3 times. For the fifth term, I'll have added 5 4 times to the first term. So it seems like t sub n is going to be 2 plus 5 times n minus 1. So 1 less than the term number. So my formula is going to be t sub n is equal to 2 plus 5 times n minus 1. And I can simplify this. I can say that t sub n is equal to 5n minus 3. Okay, so that's the explicit formula for that sequence. And one of the things to notice is that because there's this common, what we call a common difference here between all these terms, that means that I'm adding the same value, or I'm adding the same value to the previous term to get the next term. We know that this equation should be linear. Okay, so I do have a linear equation for the nth term here. Okay, so that example is not too bad. It just turns out to be a linear equation. We can look at ones that are maybe a little bit more, a sequence that has a formula that's a little bit more interesting. So here, let's see. I have a sequence where, let's try to figure out what's happening here. So we have 3 halves, then the next term is negative 4 thirds, then the next term is 5 fourths, and then the next term is negative 6 fifths. Okay, so let's think about what's happening here. So it seems like the term number, or the denominator, is increasing by 1 each time. And then the numerator is increasing by 1 each time as well. The magnitude, that is. But it's flipping signs. Okay, so let's think about this. Let's try to just represent the denominator first. So we have that in the denominator. Okay, and this is kind of what you have to do with sequences and series. You kind of just try to piece something together based on the pattern that you see. Okay, so in the denominator, we've got that the term number, or the denominator increases by 1 each time, but it's 1 greater than the term number. So we would just have that the denominator is just n plus 1, okay? So the denominator is n plus 1. So we've got, for the first term, it would be 1 plus 1, which is 2. For the second term, it would be 2 plus 1, which is 3, and then 3 plus 1, which is 4, 4 plus 1, which is 5. The numerator is a little bit trickier, but let's just compute the magnitude first. So in the numerator, we've got first 3, then 4, 5, 6, if we only look at the magnitude of the numerator. So notice that the pattern is that the magnitude of the numerator increases by 1 each time, and it's always 2 greater than the term number. So it's just going to be n plus 2. Now, we have to make sure that the numerator flips in sign each term. So what we can add is we can add a factor of -1 to the numerator. We can say n minus 2 times -1, and now we have to make it so that it's negative when the term number is, let's see, so it's positive for odd term numbers, because this is term number 1, this is term number 2, this is term number 3, this is term number 4. So and I guess we could write this as T1, T2, T3, and this would be T4. So for odd terms, it seems like the numerator is positive, and for even terms, the numerator is negative. So one way to do that is just to have -1 to the power of n. And now here, if n were 1, then this would be negative. I'd have -1 to the power of 1. So we don't want that. We want to and then if n were even, then we would have this would be positive, because -1 to the power of some even number is just positive 1. So what we can do is we can change this so that we have -1 to the power of n minus 1. And now we'll see what happens. Well, when n is odd, we'll have an odd number minus 1, which is an even number, and then we'll have -1 to the power of some even number, which is positive. And then when n is even, we'll have n to the power of some positive odd number, which is going to be negative, which is exactly what we need. So our formula is T sub n is equal to n plus 2 times -1 to the power of n minus 1 all over n plus 1.